Welcome back to AI Paper Podcasts. Today we're looking at a really interesting challenge. How do you get an AI to recognize something like a cracked bottle or suede boots that reach mid-calf, especially if it's only ever seen, say, a new bottle or maybe leather boots?
Right, that's the core idea behind Compositional Zero-Shot Learning, or CZSL. You're combining known concepts, attributes, and objects into new pairs the model hasn't explicitly been trained on.
And this paper, MSCI, addressing CIB's inherent limitations for compositional zero-shot learning, points out something kind of surprising.
Yeah, it argues that big models like CIP, while great at general image text matching, actually stumble on the fine-grained details needed for CZSL.
Why is that?
The paper suggests it's down to CIP's architecture and training. It focuses so much on the global picture that it can lose those specific local details like the crack in the bottle.
Okay, so what's the fix proposed here?
They introduce MSCI, that's Multi-Stage Cross-modal Interaction. It builds on CIP but uses its visual features differently.
How so?
Instead of just the final output, MSCI actually grabs features from different layers of CLIP's visual encoder, the early layers for local details and the later ones for the global context.
Clever, so he gets both views.
Exactly. It aggregates these, then blends them with the text description in a couple of stages. Plus, there's a dynamic fusion step to balance the local versus global focus.
And does it work?
Apparently, yes. The paper shows state-of-the-art results on key CZSL datasets, especially the ones needing more detail and in trickier open-world scenarios. It really seems to boost CLIP's ability for this specific task.
Okay, let's dig into that a bit more. Remind us again, what exactly is compositional zero-shot learning?
So think of it like this. You teach a system about individual states or attributes like tall or green, and individual objects like building or tree.
Right.
The goal is then for the system to recognize a combination it's never seen explicitly paired together during training, like a tall tree. Maybe it saw tall buildings and green trees, but never that specific tall tree example.
Yeah, that sounds genuinely difficult. You need to grasp the object, understand the attribute modifying it, and figure out how they compose visually.
All without a direct example of that exact combination. It's a tough ask.
And older methods struggled with this.
They did. Before these huge pre-trained models aligning the visual features with the text descriptions, the whole cross-modal alignment thing was a major hurdle.
Right.
And also just visually separating the feature for the attribute from the feature for the object within the image itself was tricky.
Okay, and that's where something like CLIP changed the game.
Exactly. CLIP's massive pre-training on image-text pairs gave it this really strong ability to match images and text based on their overall meaning. That's why lots of recent CZSL work has tried to leverage CLIP.
As this paper argues, there's a catch.
Yes, this is the really interesting part. They argue that the very process making CLIP good for general matching actually creates a limitation for this fine-grained compositional task.
Okay, lay it out for us. Why would CLIP have this blind spot?
They give two main reasons. The first one is architectural. CLIP's visual encoder, usually a vision transformer or VIT, relies heavily on global attention. It looks at the whole image and compresses it down into one main vector, a single representation.
Okay.
Which is great for getting the gist of the scene, but you inherently lose fine-grained local details in that compression. Things like specific textures, edges, small patterns of damage, they can get smoothed out.
So, trying to spot the difference between a smooth bottle and one with tiny cracks, that cracked texture might just get lost in the overall bottleness.
Precisely. And the second reason is linked to how CLIP is trained. Its contrastive learning objective focuses on making sure matched image text pairs are seen as similar globally and pushing mismatched pairs apart.
Right, make the dog image close to the word dog.
Yeah, but it pushes the model to capture the overall meaning to tell concepts apart quickly across millions of examples. It doesn't specifically train the model to align, say, fine local features with specific words in the description.
Ah, I see. So it learns to see bottle really well, but it doesn't necessarily prioritize learning that the specific visual feature of a crack corresponds strongly to the word cracked.
That's the argument. If the key difference, like between cracked bottle and new bottle, is just one small local detail, CLIP might just register bottle and miss the crucial state information. Its architecture might have compressed the detail, and its training didn't emphasize linking that detail to the attribute word.
That's a fascinating point. And they're saying this MSCI model is designed specifically to address that weakness.
Exactly. They seem to be one of the first to really pinpoint this specific limitation and propose using those intermediate visual layers as the solution.
Okay, so let's get into MSCI, the Multi-Stage Cross-modal Interaction model. How does it actually work? What's under the hood?
Right. So it starts with the standard CLIP backbone, the VITL14 image encoder. It takes the final layer's CLS token representation as a starting point. Then it uses some small MLPs, simple neural nets, to get separate initial visual representations for the state, the object, and the combined pair, sort of specializing the visual input a bit.
And for the text said?
They use those soft prompt templates like a photo of state object. These go through the CLIP text encoder. But the interesting bit is that the embeddings for the actual placeholder words, state, and object are treated as trainable parameters. They get fine-tuned.
Okay, standard enough so far. But where does the multi-layer magic happen?
Right here, the multi-layer aggregation part. This is the key innovation. Instead of only using the final layer features from the visual encoder, which capture that global view, they also grab features from multiple layers. Specifically, they take features from the first few layers, the early ones.
Why those?
Because those early layers are known to retain more low-level local information. Think edges, textures, basic shapes. And they also take features from the last few layers, which hold the high-level global context.
So they're explicitly grabbing both the detailed view and the big picture view. How do they combine these features, pulled from different spots?
So they take all the features from the first N layers, stack them together, concatenate them. They do the same for the features from the last M layers.
Okay, 2 stacks of features.
Exactly. Then each stack, the low-level one and the high-level one, gets passed through what they call a self-adaptive aggregator module.
What's in that module?
It's a linear transformation, then layer normalization, a ReLU activation function, and dropout. The result is 2 aggregated feature vectors. Flow representing the aggregated local details, and phi for the global context.
And why self-adaptive? What's adapting?
The self-adaptive part mainly comes from that learnable linear transform within the aggregator. It allows the module to learn the best way to combine or weigh the features coming from different layers within that stack, either the low stack or the high stack.
I see. So it learns how to best summarize the low-level details into flow and the high-level ones into phi.
Precisely. And their ablation studies later show this specific aggregator design works better than simpler alternatives.
Okay, so now they have flow, local, and phi, global. How do these get integrated with the text information?
That's the next core piece. The multi-stage cross-modal interaction. It's shown nicely in their figure 2. It happens in 2 main stages, progressively.
Walk me through stage 1.
In stage 1, they take the initial text embedding just from the prompt, like a photo of state object, and they interact it only with flow, those aggregated local features, using a cross-attention mechanism followed by an MLP. The output of this stage is called T1. You can think of T1 as the text embedding now enhanced or informed by the local details from the image.
Okay, so T1 is like the text meaning plus textures and edges.
Kind of, yeah. Then comes stage 2. They take T1, which already contains that local image information, and now they interact it with phi, the aggregated global features.
Same mechanism, cross-attention and an MLP.
Exactly the same. Cross-attention and an MLP. The output here is T2. So T2 now represents the text embedding that's been refined first by local details and then by the global context. It's a progressive enhancement.
That makes intuitive sense. Build up the understanding layer by layer. So T2 has both local and global info mixed in. How do they get the final prediction embedding from all this?
That's the last step, the dynamic fusion module. The final text embedding they use for prediction, let's call it T-final, is created by combining the original text embedding, T, the locally enhanced one, T1, and the globally enhanced one, T2.
How are they combined? Just added together?
It's a weighted sum. T-final equals T plus lambda 1 times T1 plus lambda 2 times T2.
Okay, weighted by lambda 1 and lambda 2. Are those fixed weights?
No, and this is crucial. Lambda 1 and lambda 2 are learnable parameters. They are trained along with the rest of the model. That's the dynamic part of the fusion.
So the model itself learns how much importance to give to the purely local enhancement, T1, versus the combined local plus global enhancement, T2, when forming the final representation.
Precisely. And these learned lambda weights can end up being different depending on whether the model is trying to predict the state, the object, or the full state object pair. It gives the model flexibility.
So it could learn, for example, that for recognizing cracked, the local info in T1 is really important, so lambda 1 should be high for the state branch.
Exactly. While for recognizing the general object model, maybe the global context captured later is more useful. The dynamic weighting allows it to adapt.
Okay, so pulling back, the core idea is grab features from early and late layers, process them into flow and phi, progressively inject them into the text embedding via 2 stages, T1, T2, and then dynamically learn how to best combine the original text with these enhanced versions.
That's the essence of MSCI. It's designed to give the text embedding much better sensitivity to the specific visual features needed for CZSL, overcoming that limitation they identified in standard CLIP.
Right, makes sense conceptually. How did they test it? What data sets did they use?
They used 3 well-known CZSL benchmarks: MIT States, UT Zappos, and CGQA. And they specifically mentioned that UT Zappos and CGQA are considered richer in those fine-grained details, making them good test beds for their hypothesis about local features.
And the metrics.
Yeah.
How did they measure success?
They used the standard metrics for CZSL. There's S for accuracy on seen combinations, U for accuracy on unseen combinations.
Right, so the zero-shot part.
AHM, which is the harmonic mean of S and U, giving a balance. And AUC, the area under the curve plotting seen versus unseen accuracy. They focus on AUC as the main indicator of overall performance.
And the results. Did MSCI deliver?
Yes. Looking at their main results tables, MSCI achieved new state-of-the-art performance on AUC and HM across all 3 datasets.
Wow, okay.
And this was true in both the typical closed world setting, where you only classify among the test combinations, and also the more challenging open world setting, where distractors are included.
And you said the gains were particularly noticeable on UT Zappos and CGQA.
That's right. The AUC improvements there were quite significant, which, as you said earlier, lines up perfectly with their core idea, right? Those are the data sets where subtle visual distinctions matter more.
Yeah, that makes sense. And the strong performance in the open world setting also seems important.
Definitely. When the model has to pick the correct unseen combination out from a much larger pool of possibilities, having that enhanced sensitivity to the defining local features becomes even more critical. It really seems to help reject wrong answers.
Did they investigate how many layers to aggregate? Does it matter if you take features from 2 layers or 5 layers?
They did. They have a figure showing this analysis. It turns out the optimal number of early layers, N, and late layers, M, to use does vary a bit.
Oh, how so?
For UT Zappos, which is maybe structurally simpler, using N3 and M3, first 3 and last 3 layers, worked best. But for the more complex MIT States and CGQA datasets, using N4 and M4 gave the best results.
Interesting. So dataset complexity plays a role.
It seems so, but they found that generally keeping N equal to M was a good strategy.
Okay, so the overall results look strong. But did they verify that each part of their MSCI design actually contributes? The ablation study?
Yes, they did comprehensive ablation studies reported in Table 4. They basically took the full MSCI model and then removed or changed one component at a time to see how performance dropped.
What were the key takeaways there?
Pretty clear confirmations. First, their specific self-adaptive aggregator for combining the multi-layer features performed better than simpler alternatives, like just averaging or max pooling.
Okay, so the way they combine layers matters.
Second, the 2-stage cross-modal interaction process was shown to be better than just doing a single stage of interaction. That progressive refinement seems important.
Right.
And third, the dynamic fusion module, where those lambda weights are learned, performed better than simpler static fusion methods, like just averaging T, T1, and T2.
So it really seems like all the main pieces, the specific multi-layer aggregation, the 2-stage interaction, and the dynamic fusion, are all pulling their weight.
That's exactly what the ablations suggest. Each proposed component provides a measurable benefit, and you need all of them together to get the full state-of-the-art performance.
Did they give any visual examples, like show us where it works well and maybe where it still fails?
Yes, Figure 5 has some qualitative examples.
What do they show?
The successes highlight cases where MSCI correctly identifies tricky combinations. For example, distinguishing suede boots mid-calf from visually similar options, like maybe suede boots.ankle. A model relying only on global features might miss that subtle length attribute.
Makes sense.
They also show it correctly identifying broken bottle, which clearly relies on spotting that specific local damage pattern.
And the failures, what tricks it up?
The failure case they show involves a situation with highly similar distractor images. It suggests that even with MSCI's improved local perception, if an incorrect state-object pair looks visually very close to the correct one in subtle ways, the model can still get confused, potentially misinterpreting both the local details and the global context.
So it's better, but not infallible, especially when things get visually ambiguous.
Exactly. It pushes the boundary, but some challenges remain.
Okay, so let's try to wrap this up. The big contribution of this MSCI paper seems to be identifying and addressing a specific limitation of standard CLIP for CZSL.
Right. That limitation being its relative weakness in capturing fine-grained local visual details due to its global attention focus and training objective.
And MSCI tackles this head-on by explicitly accessing features from different stages of CLIP's visual encoder, getting both local and global information.
Yep, using that multi-layer aggregation.
Then it integrates this information progressively with the text description through a two-stage cross-modal interaction,
Creating T1 and T2.
and finally uses a dynamic fusion mechanism with learnable weights to combine everything, allowing the model to adaptively balance local and global cues.
That's a great summary of the mechanism.
And the payoff is state-of-the-art performance on CZSL benchmarks, validating their approach, especially on detail-rich datasets and in open-world settings.
The results strongly support their method.
But thinking about that failure case they showed, it does leave us with a lingering question, doesn't it?
What are you thinking?
Well, if even with improved local perception, highly similar distractors can cause failures, it suggests there's still another level of challenge. How can future models, perhaps building on MSCI, get even better at disambiguation?
That's a great point. Maybe it requires more than just combining local and global features, perhaps a deeper kind of semantic reasoning, or incorporating broader contextual knowledge somehow.
Yeah, moving beyond just feature alignment to maybe a more robust understanding of how attributes realistically modify objects in the world.
It feels like that's the next frontier. How to handle those really subtle, almost misleading visual cues that require that deeper level of understanding. Definitely something to keep an eye on in future research.
Absolutely. Well, this was a fascinating look at MSCI and how it pushes the boundaries for compositional zero-shot learning. Thanks for breaking it down.
My pleasure. It's a really clever piece of work.
And thank you for joining us on AI Paper Podcasts. We'll catch you next time.